Sunshine, everyone! Today's lesson is a continuation of Chapter 5, Mathematics for Efficiency. First, let's have a recap. Last week, together with Explorer Michaela, we discussed linear programming, which involves in the linear inequalities in two variables, where we graph the two or more inequalities and we determine their coordinate systems. Then for the second, we discussed the transportation and assignment problems with Explorer, Kat, and Dana, right? Did you remember? The transportation problems we used was the northwest corner rule and the stepping stone method, while in the assignment problems, we used the Hungarian method and the maximization assignment problems. Let us now move forward.
Map! Map! 大声点!
First, we have to go through the bouncy house. Then across the piñata forest. And that's how we get to the bear's castle.
As a fellow explorer, likewise in the video, Dora used a map, and the map is a character in the show presenting Dora's companion to know the route of her destination. However, in our daily life, coming from place to another, there is a lot of possible routes you can discover. And from your discovery, you tend to do calculation, finding the best route, the way possible to get the shortest path. And that is efficient in saving money and time, especially if you are a student, a commuter, or just a normal individual. We should be conscious in handling our money and be on a budget. We are not Lisa of Blackpink to sing, "Drop some money, drop it on my money," all over the place, and waste it for nothing. A simple reminder to listen carefully as you try to help Dora to reach her destination at the end of the video. Moving forward, we should know the basic concept first. Here is a graph that represents a connection between pairs of elements. These elements with the colored circles are called nodes that represents the destination, while these lines that you see is the one that connect the nodes that is called edges. Another illustration, here you can see a comparison of two graphs. There is a simple graph and a multigraph. A simple graph has an undirected graph with no parallel edges and no loops. While you can see on the right side, the multigraph has a multiple edges between any pair of vertices or an edges from a vertex to itself, that is called a loop. Another illustration. Here you can see in the illustration, we used a graph in a transportation model where the nodes would represent facilities, here, facilities, that send or receive products, and these edges would represent the paths that connects them. Another example. Then here you can see a representation of two graphs, the undirected graph and the directed graph. Undirected graph is a graph whose edges are not directed, while the directed graph is a graph whose edges are directed by arrows. Here you can see a differences between these two illustrations. The undirected has no arrows, while the directed has an arrows. Another is a weighted graph whose edges have a weight and cost. The weight of an edge can represent distance or time between the pair of nodes it connects. Here you can see a weighted graph, and each weight has its corresponding outside the edges. Likewise, this 4, 4, 2, 1, 1, and so on and so forth. We would mainly focus in this weighted graph because these weights are essential for finding the shortest path using Dijikstra's algorithm.
It's trivia time!
Did you know that Dijikstra's algorithm was created and designed by Dr. Edgar Dijikstra in just 20 minutes? Can you imagine 20 minutes finding a shortest path in his travel from Rotterdam to Groningen, and 3 years later, it was then published in 1959. Moving forward, let us try and solve the shortest path. Come on, Babylons! Everybody, let's go!